Hi, it's me, Dr. Prasad Puthiyillam. Continue my classes on coordination chemistry, magnetochemistry of coordination compounds. In previous class, I explained about the introduction, types of magnetic behavior, orbital contribution to magnetic moment, spin orbital coupling, and this class explaining about spin crossover systems. So before explaining crossover system, in previous class I explained about the spectroscopic term, how to write the spectroscopic terms. That is when L is equal to 0, it becomes S. When L is equal to 1, it becomes P. So the corresponding Mulliken's terms also mentioned here or given here. This is required to explain. I need this Mulliken's terms to explain the spin crossover systems. Okay, so for S, it is mentioned as it is given as A1G, and if it is a tetrahedral complex, that is A1. For P, it becomes T1G and T1, so on. So, spin crossover system. The spin crossover system was first observed in 1931 by Campy and his co-workers who discovered anomalous magnetic behavior, that is different magnetic behavior for tris NN dialkyl thiocarbamate 3 complex. The structure is given here. The spin nature of this complex, okay, this complex means we can substitute here the n derivatives can be changed. So the spin nature of these complexes were sensitive to the nature of the amine substituents. So here whatever the substituents present here, that will decide the spin crossover. The different properties are observed with this particular complex, that is work by Campy and his co-workers. The spin crossover or spin transition or spin equilibrium behavior, it is a phenomenon that occurs in some metal complexes. The spin state, that is high spin to low spin states of the complexes, changes due to some external stimulus or external stimuli such as variation of temperature, pressure, light radiation, or influence of a magnetic field. So spin crossover refers to the transition between high to low or low to high spin states, which is say mentioned here. So here this represents the spin crossover system, the where the spin changes from high spin to low spin, or high spin to low spin, or low spin to high spin states. This phenomenon, it is commonly observed with some first row transition metal complexes, that is 3D series, with D4 to D7 electron configuration in octahedral ligand geometry. As, as you know that metal ions with any of the D4 to D7 configuration exhibited two possible electron configuration, that is high spin configuration as well as low spin configuration in octahedral ligand field, not in tetrahedral ligand field. So some of the example of metal ion that can exist in high spin or low spin state in octahedral ligand based on the field strength of the ligand, weak field ligand or strong field ligand. It is the cobalt CO3 plus, CO2 plus, Fe3 plus, and Fe2 plus. It's a low spin or high spin state is decided by the nature of ligands that are coordinated to the coordination complex, whether it is weak field ligand or strong field ligand. Okay, so the considering the low spin complex, say case of Fe2 plus, if I take the example, consider the low spin complex of FeCN6 4 minus with the ground state Millikan symbol of 1 Ag1, and a high spin complex of FeF6 4 minus with the Millikan's symbol of 5 T2G of iron 2 plus ion. It is a D6 system. So the Tanabe-Sugano diagram, it is given here. Based on that, we can say that now a change in temperature, will lead to an alteration in population of two spin states. The Tanabe-Sunago diagram of the two complexes reveals that if the ground state of the complex is low spin, then an increase in temperature will increase in the population of high spin state, that is magnetic susceptibility will increase. Whereas a decrease in temperature will increase the population of the low spin state, that is magnetic susceptibility will decrease. Okay, so the Tanabe-Sugano diagram of this D6 complex also shows that near the crossover point between weak field and strong field, the difference in energy between the spin-free 5T2G and spin paired 1A1G ground states become very small. So within this region, it is reasonable to expect that both the spin states may coexist in equilibrium, and that the degree to which each is represented will depend on the temperature. That means delta O, that is octahedral crystal field splitting minus pairing energy P is equal to K into T, where K is a constant, T is the temperature. The most important example or interesting example for a spin crossover system is Fe110 phenanthroline and NCS complex. And the structure is given, structure of the complex is given here. At high temperature, it exists as high spin with 4 unpaired electrons. Uh, and the magnetic moment is consistent with the 4 unpaired electron. The magnetic moment is found to be consistent for the unpaired 4 unpaired electron, and it is a almost constant value. But as the temperature is lowered, a sharp drop in magnetic moment is observed. The temperature is as the temperature decreases. So you can see that this is a high spin state and having high. This is the state with a high magnetic moment. As the temperature decreased, uh, as the temperature is lowered, a sharp drop in magnetic moment is observed. And below 175 Kelvin or below 174 Kelvin, the low spin form of complex becomes dominant. That means above 174 Kelvin, it becomes a high spin, and below 174 Kelvin, the complex is becomes a low spin complex. So spin crossover phenomena, it can be represented by these uh, say electronic configuration. It is represented here that when it is a low spin complex, that means paired electrons, there is no spin or electron is zero, and magnetic moment is also zero. Whereas here it is a high spin situation. Its magnetic moment, this is a D6 system, magnetic moment will be around 4.9 Bohr magneton. Considering the spin transition curves, the spin crossover phenomena, it can be represented by spin transition curves. In spin transition curve, the temperature it is plotted versus high spin molar fraction, that is given here. How it can be calculated, for say example for iron, the high spin molar fraction can be calculated as the high spin state of iron divided by total spin of iron, or high spin state of iron divided by high spin state plus low spin state. Like that we can calculate the high spin molar fraction. It is plotted against the temperature. These curves indicates that a spin transition has occurred in a metal complex as the temperature is changed. Okay, so spin transition, it is based on the temperature, it is mentioned. If you take the first case, that is gradual transition, the gradual transition curve is an indication that not all the metal centers within the complex are undergoing the transition at the same temperature. Okay, so when we say about a particular complex, say iron 110 phenanthroline NCS complex, you take the example, not only one molecule is there, so many molecules, complex molecules are there. So all the metal ions, the central metal ions are not participating in the transition in an equal manner. That's why all metal centers within the complex are undergoing transition at a different temperature. That's why we are getting a gradual transition. Whereas the second case, the abrupt transition with hysteresis, here the abrupt spin change indicates a strong cooperativity. Cooperativity means we can call it as even communication. Communication between the different metal ions, uh, and this communication between the neighboring metal complexes, and here that material can exist in two different spin states with a different range of external stimulus or external stimuli. The third one, or two-step transition, is relatively rare. Uh, this type of transition is relatively rare. For example, if you take, say, a dinuclear spin crossover systems or spin crossover complexes, for which the spin transition in one metal center opposes the spin transition in second metal center, so that we are getting a stepwise manner transition, or equal it as a two-step transition in case of a spin crossover system. Some of the factors which are affecting the spin crossover system or the effect of a spin crossover system on chemical as well as physical factors. The factors are listed here. I'm not going explaining in detail. The effect of metal ligand bond distance, effect of intra-ligand substitution, effect of counter ions, non-coordinated solvent molecules, hydrogen bonding, metal dilution, or the chemical factors, and the physical factors if you consider the effect of applied magnetic field, effect of sample preparation, effect of the pressure are the physical factors related to spin crossover system. So in conclusion, I would like to say that for a spin crossover system to occur, the electronic configuration should be D4, D5, D6, D7. Only in D4, D5, D6 and D7. Even D4 is somewhat rare. D5, D6, D7 are more spin crossover systems are observed. There, the system can have both high spin complex as well as low spin complex based on the ligand strength. Whereas D1, D2, D3, it is not possible. The high spin and low spin states are not possible. Even for D8, D9, and D10 configurations also, it is not possible. Uh, the second condition or to occur the spin crossover system to occur, that it should be octahedral complex. In tetrahedral complex, we know that the splitting energy is too low. That is explained in my previous classes. In tetrahedral complex, the splitting energy is too low that it always form high spin complex. So it cannot be changed to low spin. Always it prefer to be in high spin complex. Therefore, only octahedral complexes are giving spin crossover systems. Ligand should be in middle of a spectrochemical series. You know what is spectrochemical series? Based on the strength, the field strength of the ligands, we arrange the ligands in the decreasing order or increasing order. The ligands that we use in a particular complex, if should give spin crossover system, is it should be in the middle of a spectrochemical series. That means it should not be a too weak donor ligand or too strong donor ligand. Next condition to spin crossover system, it is observed only in 3D metal complex series. In 4D as well as 5D metal series, the low spin complex, they are low spin complex because of the arrangement of electrons and presence of the ligand. In 4D and 5D, they always form low spin complex. And in those cases, 4D and 5D cases, the spin crossover system, spin crossover, that phenomena, it is not observed. So that's about spin crossover system. Hope you understood this topic in detail. In coming classes, connecting to this, the topics will be discussed. Thank you very much for watching my video, and have a nice day.